very much for having me here. It's very nice to meet you all. My name is Liangxiu Han. You can call me Liangxiu or Han, whatever you feel comfortable. I'm Professor of Computing Science from Manchester Metropolitan University. So here is my contact address. So if you want to contact me, please do email me. Okay, so today's talk, I'm going to talk about meeting societal challenges using big data-driven approach. So scalable learning from big data. Okay, so maybe I should have these slides later. So what happens in the internet minute? So as you can see, everyone can get these slides from the internet. So here is the source. You can see this 2024, you can see the data from different media, for example, TikTok, and also the social media, Twitter. And you can see the data is always growing. And the data never sleeps. Actually, here we can see from the 2017, and that one is 2023. You can see the data keeps growing. So we're actually already into the very big data era. So for this type of data, we really need to understand this big data. So what are challenges of that big data? So when we talk about the big data, we really talk about data volume, data variety, and data complexity. So here we have a bunch of very big size of data set, and then as a computing scientist, what if we want to get the insight from this large amount of data set? We need to have a very the efficient data processing and data analysis technologies that can actually get the high value from this data, big data. So from technical side, what are those technical challenges for the big data? So technical challenges, the first one is that how to filter and reduce the amount of data, enable timely insight and the decisions to address the societal challenges. So that's actually come to our discipline is how we develop efficient data analysis skill. So basically it's computational modeling. For whatever reason now you say big data analysis, AI. So that's deep learning, machine learning. So that's all belong to this category. So basically is all what we do is that the first thing, if we want to build efficient data analysis method, that's to try to filter and reduce the amount of data, enable timely insight decision. And then secondly is how to process such big data to efficiently, for example, how we move the data, whether we want to move the data closer to the program or whether we want to move the program to the data. So that's we looking at the data processing and the system architecture, for example, parallel and distributed computing, and even from grid computing to the cloud computing. Okay, so that's kind of thing we really focus on. When we talk about the big data, we really focus on data analysis and scalable infrastructure. So our big data research is really along this line. We focus on both fundamental and applied research in big data and analytics. So in the past years, they often talk about the data-intensive computing. So data-intensive computing, you try to build the architecture. And so we also, to demonstrate our big data technologies, we try to apply this big data into the different domains. So for example, in the precision agriculture, healthcare, or even the smart cities. So we try to build the capability and the capacity to handle and process the different type of data, from images, text, to the time series data or geospatial data. So scientifically, we aiming to develop methodologies to handling different data. Practically, we really want to build a scalable data product, because we don't want just publish paper, develop methodology, but we really wanted to have translate these kind of technologies into the real world impact. So here it shows the overview of the picture, what we have been tapping into it. So here we have a different data set we are currently handling. And then we have a big data platform from edge to cloud computing, parallel distributed computing, and then with the different application to the different field. So the data, what we are currently handling, for example, satellite data, and drones data, and also the healthcare data, for example, biomedical imaging, robotics data, and mobile phone. So try to develop a lightweight edge computing, efficient edge computing algorithm. Okay, so here is just to show some example what we have been focused on. First, some selected project what we have been completed and ongoing project, where we look at, for example, the life sciences, healthcare. So where we look at developing innovative AI technology, AI solution to detect the screening the eye disease. And then we also using big data to actually identify the novel risk factor for the heart disease. And we also developing the computer-aided novel deep learning, explainable deep learning method to actually detect brain disease. And also certainly we this different project where we're looking at into the using different, for example, biomedical scans and the time series data to really looking into to address the real world problem. And then for the precision agriculture, here same again. So we're looking into the combined. For example, the first one we're looking into the combined the theoretical process-based modeling and machine learning model to with application into the precision agriculture. For example, crop yield prediction to address the societal challenges, food security. And then we also using the data from robot and drones collected from field to detect nutrient deficiency to actually to show to give the best advice to farmers, say, okay, which field you have your nutrition deficiency or sufficiency, so that give you best the advisor, give the timely decision. And certainly we also have using the different data, for example, soil temperature, the images for the crop disease detection, using developed mobile app to actually to give the live detection for the farmer, so that farmer doesn't need any expert in the field. Even like in the rural country, for example, particularly in the rural country where there is no cloud, and how can you do that? So that's why we developed this lightweight computing algorithm where you can actually directly use the mobile app to get the disease detected immediately. Certainly for the rail, we also focus on using the deep learning models, develop a lightweight deep learning model to detect the rail so to detect underneath the defects, to understand the rail infrastructure, to provide the inspection of maintenance. Okay, so here are some of our example working prototype. So if you are interested, you can have a look at this already, the working prototype. So we're working very closely with the farmers and with the end user, where we develop a big data platform for the solution. So these are the examples. So for example, we already have this mobile app, globally already on the Google Play Store, so everyone can download. So you can see here we process the edge computing, develop lightweight deep learning model, and where the second one we use drone data, we we give the 2 levels classification. The first level, we give the disease distribution map using the deep learning model. And then the second level, give the high resolution distribution map so that the farmers can see. And then the same way for the nutrition detection. So all these things, what we really bear in our mind, our ultimate goal is really to address the societal challenge using big data. So that's why this is our, this shows our, along this path, that's what we do, yeah. Okay, so here is the mobile app, what you can actually download. We also used our project data to contribute to global knowledge generation. Here we are currently holding the global competition for using the AI in agriculture, precision agriculture. We provide some high spectral data from drone, so you can use that data to participate in this competition. But even if you don't participate, that's fine. You still can use this data for your research. So, so that's very, very useful. So we already hold the 2 years this year. This year is in conjunction with the flagship the conference called International 27th International Computing Vision Conference on Pattern Recognition. So this year in India, so that's quite good conference. Right. Okay. So that's said. Because due to the time limitation, I cannot cover every area what we have done. But today, I only cover the application to the life sciences for healthcare. For the future, maybe I can cover for precision agriculture. Okay, so why today I came this work? So this work actually was funded by Royal Society Academy of Medical Science, where Newton Fund project. We're looking at the fundamental method and application method. So how we develop, as we just already mentioned, how we develop efficient big data analytics. Secondly, how we develop a scalable architecture that can facilitate such big data running efficiently on whatever back-end system, or even like from edge to cloud, okay? So this is our really goal. Right, typical deep neural networks require a large amount of data to learn the parameters, so often reaching to millions, particularly, you know, current large language model, right? They requires huge computational power. So training a deep learning model is really both computational and data intensive, which may take few days or weeks or maybe months. So longer research and production cycles. So when we talk about, so that's why our research aim is really to investigate how we develop a scalable deep learning models. So scalability of deep learning, by scalability we mean that implementation in both hardware and software to allow the computation enhance the model performance in a cost-effective manner. So several main principles when you actually try to focus on this area. So from model development point of view, so we always wanted to reduce the parameter and the size of the model, and also optimization, or even you do the quantization, right? And from system architecture point of view, so we wanted to actually to build parallel and distributed computing. Now certainly if you don't have any way to actually in a very quick short way to advance your hardware. So that's the best way to actually make your the computing program more scalable. So when we talk about parallel computing, there were three the major principles what you should really bear in mind. The firstly, so we would thinking that how we develop distribute workload or decompose the algorithm into the parts. For whatever, for example, deep learning, you have a big deep learning model, you might want to decompose this into the part. And then the second one is how to map the task onto various computing nodes and execute in a parallel. So basically map the job to the computing resources. And then how to coordinate and communicate subtasks to those computing nodes. So these are really major principles when we actually consider scalable computing architecture. So along this line, that's why when we investigate this project, we actually try to focus on this perspective. Firstly, we develop efficient machine learning or deep learning model to process, analyze the neural imaging data, because that's all structured medical image scan. And then we wanted to scalable our algorithm. We parallelize this algorithm based on the previous principle, what we did. So that's to efficiently, for efficient learning in parallel the fashions. Okay, so why we do this topic, okay? So this topic is very, we go to this project. That project is really, we look at address the societal challenges, the Alzheimer's disease. So because this disease is most commonly caused dementia, affect over 30 million individuals. It cannot be cured, but it can be slowed. So if you actually really, the progress can be slow if you have appropriate therapy, okay? You can see why we actually develop such method, use this. As you can see here from this picture, you can see if normal brain image, scanned image like this, you can see, but the on my left-hand side, where you can see that's abnormal, you have Alzheimer's disease. You can see there is obvious the hole, right? You can see, so from this side, you can see computing vision may be the good way to identify such hole, right? So the difference between. So that's why we develop the computing vision, computing aided method. So in the clinically structured magnetic SMRI scan is often used for AD diagnosis. So it is non-invasive, and in current practices, the clinician, they just use the images, what I just showed the previous slides. They just say, oh, right, you have this Alzheimer's disease. But that's all manually, right? It's not automatically. So that's why computing-aided diagnosis come out. And then here, we normally, if we want to identify this disease, in our research domain, so we normally looking at two types of the tasks. One task is normal. We identify whether you're normal and abnormal. The secondly, how the progressive, the extent of the progressive. So for example, progressive MCI or stable MCI. So that's it, whether you slow progress, whether you stable progress. So that's normally, we converted diagnosis task into our machine vision task into these two types of tasks. So the challenge, because structured MRI scan is 3D data, yeah? So it's very, data size is 100 times more than the traditional 2D images used in common CNN models. And since the convolution, and also convolutional operator has a local receptive field, long-range dependencies can only be processed after passing through the several convolutionary layers. This could prevent learning that long-term dependencies. So that's the most existing work, what they do. So that's why we proposed the 3D explainable residue attention network for the deep learning neural network that adopts self-attention residue mechanism and explainable gradient-based localization, class activation mapping. So this work actually currently is highly cited. So because when we did this work, it's very first few papers, first few work we have done. So that's we use the grid cam. Now certainly now there is a lot of more visualization, explainable mechanism already. So this is what we have used, developed architecture. So this, so I'm not going to go to the detail. And then the design rationally, so as we mentioned, so for example, why we introduced the residue mechanism. So this is because we can ease the problem of vanishing exploding the gradient. When a network goes deeper, so in addition, the residue connection, they avoid the loss of global features to ensure the integrity of the original information. And the self-attention mechanism, it can actually to learn the long-range dependency. So most the existing, now we commonly use the CNN, they cannot learn the long-range dependency. So that's why we introduced the self-attention mechanism. And we use gradient-based localization class the mapping, and went to the explanation of prediction of the Alzheimer's disease. Okay, so here is a specific technical detail. So I'm not going to talk more detail, but if you're very interested in this being published in journal, IEEE Journal of Bioinformatics. So here are the modules. Okay, let's see so here here is just the more detailed explanation. We use the 3D grid cam to explain the module design decision. So as you can see, so here we use the data from US, the ADNI. This is a very famous big data set. Used for particularly for brain disease diagnosis, the data. So if you're interested, free for use, but you need to register. And then the most our researchers in this field, they all use this type of data. As you can see here, our proposed method is so our proposed method for the two tasks. The first one is classification of abnormal and normal cohort. And then the second one is progressive, the status. So as you can see, our proposed method is performed much better than the traditional, the existing, the state-of-art technologies. Yeah, this is the result. And we also actually examined the ground truth data. As you can see, our algorithm can actually, accurately identify those wrong labeled data. And so, this shows our performance. Yeah. Okay. Here is we use the different independent data set, not the training and. Not so completely independent data set for testing our models. Right, okay, so that said, previously we developed such deep learning models, but that doesn't work maybe, because that's maybe only work on the one single work GPU, GPU station, right, one GPU card. May not work in Scalable. So that's why we need to consider how we actually make it scalable. So in the parallel computing field, we look at parallelization. For example, there is 4 types of, for example, data parallelization. You just decompose your data into the chunks. You just through into the different computing nodes without changing any of your program. You just copy your program into the different computer. You just compute in parallel. And then the model parallelization, you split the DNA model into the different partition and place them into the multiple devices with the same mini batch. And the pipeline parallelization, you break the computational task into the sequence of process stage. Each stage takes the result from the previous stage as the input. and then hybrid parallelization. So combine 2 or more of the parallelization for distributed training of neural networks model. So model parallel and data parallel. So in our case, we use a hybrid parallelization. So that's why we developed a generic full end-to-end hybrid the parallelization approach for the multiple GPU distributed training of deep learning models. So where we split a DNA model into the independent partition and formulating the network partitions and the GPU allocations problem as a one multiple knapsack model. This is most famous model commonly used. Propose a genetic algorithm, a resource allocation mechanism. As you already see in my previous slides, you need to think about how to map your resources to the, how to map your tasks into the different resources. And then we evaluate. And then I think this is our model. As you can see, we have a data parallelism, we have a genetic algorithm, and then we have a model parallelism combined together, and then we make this is system overview. And we use this what we call all reduced mechanism from parameter update. All GPUs are logically arranged in a ring or reduced topology. Each GPU send and receive required information to update its model parameter. But certainly this is much more involved technical. We already also published this paper in the journal so that you can have a look at. And we also, when we're doing the network partition, so this is come to the model part. We decompose the model algorithm into the different part and then send this different part into the different computing nodes. And then the, here is the algorithm, what we used, and then the, here is architecture. We test our model on the Amazon GPU. We rent the GPU with 8 nodes, the 8 GPU very large instance. So basically the result, I just want to show you the result. As you can see, the blue line is our proposed method. So it significantly reduced the time. Right, so I think the, this is, in our parallel field, we often look at the speed up. Say, for example, based on this linear relationship, and we can see whether it is your method is scalable. So if the close to the linear, that said, your method is scalable. So that's why you can see our model is very scalable. Okay, so I think we also compared most advanced the architecture, the model, for example, like a greedy learning DGL, and also other methods, layer-wise, the staleness and diverse stale parameters. So all this model is advanced architecture, advanced state-of-art technologies. Yeah. Okay, so I think the time up, but I think we do have another very interesting work we call the layer-wise partitioning and merging for efficient and scalable deep learning. This one is actually even the more advanced than previous one. So basically, this is developing the looking at the neural network, how we actually break solve the problem for the solve the problem for the how we decompose our deep learning models into the part. So this is this paper has been published in the Future Generation Computer System. So if you're interested, please do have a look at. I think this is very good. Good work. But I think, my time is up here. I'm sorry, so I haven't been able to finish. Yeah, thank you.
Okay.
Yeah.
Professor.